21ページからで、こっちもいけてるかな。21ページからいきます。それでどうしようか。ここから、PDF ここにあります。でダウンロード、で21ページからやります。21ページどこだ。プラズマ周波数のちょっと難しい感じのとこだったんですけれども、結構いったな。はいはい、これが、サーマーコンダクティビティ、ローレンツナンバーです。だいたい 2.22 ぐらいになっていると。で、止まっちゃった。As a concrete example, let us examine a case where the temperature drop is uniform in the x direction. In the steady state, the thermal current will also flow in the x direction and have a magnitude jq equal minus kappa dt dx. To calculate the thermal current, we note Assumption 4, page 6, that after each collision, an electron emerges with a speed appropriate to the local temperature. The hotter the place of the collision, the more energetic the emerging electron. Consequently, even though the mean electronic velocity at a point may vanish, in contrast to the case where when an electric current flows, electrons arriving at the point from the higher temperature side will have higher energies than those arriving from the lower temperature side, leading to a net flow of thermal energy toward the low temperature side. Figure 1.6. To extract a quantitative estimate of the thermal conductivity from this picture, consider first an oversimplified one-dimensional model in which the electrons can only move along the x-axis, so that at a point x, half the electrons come from the higher temperature side of x, and half from the low. If I don't know how to call this in English. 花文字 E of T is the thermal energy per electron in a metal in equilibrium at temperature T. Then an electron whose last collision was at x prime will, on average, have a thermal energy E of T at position of x prime. Electron whose last collision was at x prime will, on average, have a thermal energy of epsilon T at x prime. The electrons arriving at x from the higher temperature side will, on average, have had their last collision at x minus vt and will therefore carry a thermal energy per electron of size epsilon t at x minus b tau. Their contribution to the thermal current density at x will therefore be the number of such electrons per unit volume, n over 2, times their velocity, v, times this energy, or n over 2 v epsilon of t at x minus vt. The electron arriving at x from the low temperature side, on the other hand, will contribute n over 2 minus v times epsilon of t at x plus v tau. Since they have come from the positive x direction and moving toward negative x, adding these together gives JQ equal 1/2 NV. Epsilon of t at position x minus v tau minus epsilon of t at position x plus v tau, provided that the variation in temperature over a mean-free path is very small. We may expand this about the point x to find J of Q, JQ equal mv nv square tau times d epsilon dt times minus dt dx. Let me read the 29. Its change in L is L over L times the change in the sample length. Its change in L okay. Variation in temperature over mean-free path is very small. Temperature's change in L is capital how do you call this? 引体 L divided by capital L. Flower lettuce. Decorated initial letter. Decorative letter. Decorated small l. Decorated lowercase l divided by capital L times the temperature change in the sample length capital L. To go from this to the three-dimensional case, we need only replace v by the x component vx of the electronic velocity v and average over all directions. Since vx square expectation value equal vy square expectation value equal vz square expectation value equal one third v square, and since n d decorated E divided by dt equal capital N divided by V, d decorated E divided by dt equal dE divided by dt divided by V equal CV. C sub V, the electronic specific heat, which is electronic specific heat, we have JQ equal one third V square tau specific heat C of V times minus nabla T gradient T kappa equal one third V square tau CV equal one third LV CV. I think usually we write this way. We write L rust. Usually we write one third CVVL. I think this is the Kittel, the order adopted in Kittel, where V square is the mean square electronic speed. We emphasize the roughness of this argument. We have spoken rather glibly about the thermal energy per electron carried by a particular group of electrons, a quantity one might be hard pressed to define with precision. Thermal energy per electron carried by a particular group of electrons, a quantity one might be hard pressed to define with precision. Hard pressed. Sorry. Hard press. せき立てられた。We have also been quite careless about replacing quantities at various stages of the calculation by their thermal averages. One might object, for example, that if the thermal energy per electron depends on the direction the electron comes from, so will their average speed, since this too depends on the temperature at the place of their last collision. We shall note below that this last oversight is cancelled by yet another oversight, and in chapter 13. Footnote 30. Footnote 30. In equilibrium, the velocity distribution is isotropic. Correction to this due to the temperature gradient are exceedingly small. We shall find by a more rigorous argument that the result 151 is quite close to, and in special circumstances, precisely the correct one. We shall note below that this last oversight is cancelled by yet another oversight. And in chapter 13, we shall find by a more rigorous argument that the result 151 is quite close to, and in special circumstances, precisely the correct one. Given the estimate 151, we can derive another result independent of the mysteries buried in the relaxation time tau by dividing the thermal conductivity by the electrical conductivity. We shall note below that the last oversight is cancelled by. Okay. So this last oversight is this one. Anyway. Given the estimate 151, we can divide another result by independent of the mysteries buried in the relaxation time tau by dividing the thermal conductivity by the electrical conductivity 1.6. Kappa divided by sigma equal 1/3 C sub v mv square divided by ne square. It was natural for Drude to apply the classical ideal gas law in evaluating the electronic specific heat and mean square velocity. He therefore in effect took Cv to be 3/2 nkb and 1/2 mv square in effect took Cv to be 3/2 nkb and 1/2 mv square to be 3/2 kbt, where kb is Boltzmann constant 1.38 times 10 to minus 16 elg per Kelvin. This leads to the result. Then let me see. This one here, mv square is here. No, sorry. We put this one to mv square. So n can be cancelled. N can be cancelled. So okay. The right side of 153 is proportional to t and depends only on the universal constants kb and e, in complete agreement with the law of Wiedemann-Franz. Equation 1.53 gives a Lorentz number kappa divided by sigma t equals 3/2 kb divided by e square equal 1.24 times 10 to the minus 13 elg per ESU Kelvin square, or 1.11 times 10 to the minus 8 watt ohm per K square, which is about half the typical value given in table 1.6. In his original calculation of the electrical conductivity, Joule erroneously found half the correct result, as a result of which he found a value kappa divided by sigma t equal 2.22 times 10 to the minus 8 watt ohm divided by K square, in extraordinary agreement with experiment. This success, though wholly fortuitous, was so impressive as to spur further investigations with the model. It was, however, quite puzzling, since no electronic contribution to the specific heat remotely comparable to 3/2 nkb was ever observed. It was, however, quite puzzling, since no electronic contribution to specific heat remotely comparable to 3/2 nkb was ever observed. Indeed, at room temperature, there appeared to be no electronic contribution to the specific heat measured at all. In chapter 2, we shall find that the classical ideal gas laws cannot be applied to the electron gas in a metal. In chapter 2, we shall find that the classical ideal gas law cannot be applied to the electron gas in a metal. Drew's impressive success, aside from his factor of 2 mistake, is a consequence of 2 errors of about 100 that cancel. At room temperature, the actual electronic contribution to the specific heat is about 100 times smaller than the classical prediction, but the mean square electronic speed is about 100 times larger. We shall examine the correct theory of the equilibrium thermal properties of the free electron gas in Chapter 2 and shall return to a more correct analysis of the thermal conductivity of a metal in Chapter 13. Before leaving the subject of thermal transport, however, we should correct one oversimplification in our analysis that obscures an important physical phenomenon. Okay. Footnote 31. Since Joule per Coulomb square is watt per amp square equal watt ohm, the practical units in which Lorentz numbers are quoted are often called watt ohm per Kelvin square instead of Joule Coulomb Kelvin, Joule per Coulomb Kelvin square. We calculated the thermal conductivity by ignoring all manifestations of the temperature gradient except for the fact that thermal energy carried by a group. We calculated the thermal conductivity by ignoring all manifestations of the temperature gradient, except for the fact that thermal energy carried by a group of electrons depends on the temperature at the place of their last collision. But if electrons emerge from a collision with higher energies when the temperature is higher, they will also have higher speeds. It would therefore appear that we should let the electron's speed v, as well as the contribution to the thermal energy, depend on the place of the last collision. Okay, I think this part is this one. Here he say this part. One might object, for example, that if the thermal energy per electron depends on the direction of electrons come from, so will their average speed, since this too depends on the temperature at the place of their last collision. And we shall note below that this last oversight is cancelled by yet another oversight, this part. This part is now explained. So here we calculated the thermal conductivity by ignoring all manifestations of the temperature gradient except for the fact that thermal energy carried by a group of electrons depends on the temperature at the place of their last collision. But if electrons emerge from a collision with higher energies. When the temperature is higher, they will also have higher speed. It would therefore appear that we should let the electron speed v as well as its contribution to the thermal energy depend on the place of the last collision. As it turns out, such an additional term only alters the result by a factor of the order of unity. Additional term only alters the result by a factor of the order of unity, but we were in fact quite right to ignore such a correction. なんででしょうか。We were. It is true that immediately after the temperature gradient is applied, there will be a non-vanishing mean electronic velocity directed toward the low temperature region. Since the electrons are charged, however, this velocity will result in electric current, but thermal conductivity measurements are performed under open circuit conditions in which no electric current can flow. Therefore, the electric current can continue only until enough charge has accumulated at the surface of the sample to build up a retarding electric field that opposes the further accumulation of charge and hence precisely cancel the effect of the temperature gradient on the electronic beam velocity. When the steady state is reached, there will be no electric current flow, and we will therefore correct in assuming that the mean electronic velocity at a point vanishes. Let's see. Footnote 32. See the analogous discussion of the genesis of the whole field on page 12. Genesis. Genesis 創世記 Origin. Let me see. It is true that immediately after the temperature gradient is applied, there will be a non-vanishing mean electronic velocity directed toward the low temperature region. Since the electrons are charged, however, velocity will result in an electric current. By thermal conductivity measurements, but thermal conductivity measurements are performed under open circuit conditions in which no electric current can flow. Therefore, the electric current can continue only until enough charge has accumulated at the surface of the sample to build up a retarding electric field that opposes the further accumulation of charge, and hence precisely cancel the effect of temperature gradient on the electronic mean velocity. See analogous discussion of the genesis of whole field on page 12. When the steady state is reached, there will be no electric current flow, and we will therefore correct in assuming that the mean electronic velocity at a point vanishes. In this way, we are led to consider another physical effect. A temperature gradient in a long thin bar should be accompanied by an electric field directed opposite to the temperature gradient. The existence of such a field, known as the thermoelectric field, has been known for some time. The Seebeck effect. The field is conventionally written as E equal Q temperature gradient, and the proportionality constant Q is known as the thermal power. To estimate the thermal power, note that in a one-dimensional model, the mean electronic velocity at a point x due to the temperature gradient is VQ equal 1/2 V of x minus Vt minus V of x plus Vt. Equal minus tau V dV dx V square V of, this is a function. This is a variable. So V of this position minus V of this position. So we have this tau V. This is minus tau d dx. V squared over 2. To estimate the thermal power, note that in a one-dimensional model, the mean electronic velocity at point x due to the temperature gradient is this. We can again generalize to 3 dimensions by letting v square go to vx square and noting the x square expectation equal vy square expectation equal vg square expectation is 1/3 v square, so that vq is minus tau over 6 dv square dt gradient t. The mean velocity due to the electric field is v equal minus E tau divided by m. What is this? The discussion leading from 149 to 150. Anyway, see the discussion on page 7. To have VQ plus VE equals 0, we require that Q is a Q. E delta T. Okay, let's do this. So this is more like this thing is E over Q. So we see a Q. Then we can see this cancel, tau cancel. So Q equal 6m E dv square dt. We will put 6 upstairs. This is like 3e1 d mv square divided by 2 dt. Then I think, okay, so this thing equal NCV. This result is also independent of the relaxation time. Duluth evaluated it by another inappropriate application. Inappropriate application of classical statistical mechanics, setting CV equal to 3nkV over 2 to find, so this guy go to here. To find Q equal KB over 2E equal minus 0.43 times 10 to minus 4 volt per Kelvin. Observed metallic thermal powers at room temperature are of the order of microvolt per degree. So I think this is 43. This is more like 43 microvolt per Kelvin. Observed metallic thermal power at room temperature are of the order of microvolts per degree, a factor of 100. Factor of 100, maybe factor of 40, 43. Anyway, factor of 100 is smaller. This is the same error of 100 that appeared twice in Drude derivation of the Wiedemann-Flat's law, but being now uncompensated. It offers an ambiguous evidence of the inadequacy of classical statistical mechanics in describing the metallic electron gas. With the use of quantum statistical mechanics, one removes this discrepancy. However, in some metals, the sign of the thermal power, the direction of the thermoelectric field is opposite to what the Drude model predicts. This is as mysterious as the discrepancies in the sign of the Hall coefficient. The quantum theory of solids can account for sign reversal in the thermal power as well, but one's sense of triumph is somewhat tempered in this case. For a really quantitative theory of thermoelectric field is still lacking. Let me see. This is as mystery. The quantum theory of solid can account for a sign reversal in the thermal power as well, but one's sense of triumph is somewhat tempered in this case. For a really quantitative theory of thermoelectric field is still lacking. For a really quantitative theory, thermoelectric field is still lacking, even with quantum theory. We shall note in later discussions some of the peculiarities of this phenomenon that make it particularly difficult to calculate with precision. We shall note in later discussions some of the peculiarity of this phenomenon that make it particularly difficult to calculate with precision. We shall note. These last examples have made it clear that we cannot proceed very far with a free electron theory without a proper use of quantum statistics. This is the subject of Chapter 2. Okay, so we will try problems next time. So we stop 25, page 25.